Hi guys, welcome to Algorithms Made Easy. Today we will see the question number of 1 bits. Write a function that takes an unsigned integer and return the number of 1 bits it has. This problem or this particular thing is also known as Hamming weight. The follow-up given with this question is that if the function is called many times, how would you optimize it? In the example 1, we see that there are 3 number of 1 bits and so the output is 3. While in the second example, there is only 1 present and thus the output is 1. In the third example, there are 31 set bits and thus the output is 31. Now let's go ahead and see how we can solve this question. The first approach is looping on each bit and counting if it is a set bit. So let's take this example, and here given n equal to 11, that is 1011, I'm just taking 4 bits for now, but in the actual scenario it would be a 32-bit integer. So we will have zeros on the left. So let's take this example, and we know that when we perform an AND operation on a bit, it gives a resultant 1 when both the numbers are ones. For example, here this both are 1 and so 1 and with 1 will give me a 1. This can be useful for finding whether the bit is set or not. So this is what we are going to use in the first approach. So let's see what we are doing over here. We are taking the number and we are taking a mask. A mask would be a number that has a 1 in the bit position that we are going to check. So we'll start with the last bit and we'll keep on shifting this 1 bit one place in the left in each time we are looping it. So this shifting of 1 bit would eventually turn out as checking of that particular bit position in our original number. So in this first one, we are checking this number, and since this is not equal to 0, which means there was a 1 present, so we increment the count. Now we take another mask wherein we shift the mask 1 bit to the left and check the second bit. Since this is also 1, we'll get a 1 in the result also. And so the result would give a non-zero number. And since we have a non-zero number, we increment the count. Similarly, we check for third bit, and here as the bit was 0 in our original number, we have got a result to be 0. And so we do not increment the count and move further, checking for the other bit. And here we get a non-zero number and we increment the count to 3. So what we are doing here is we are taking a number, a mask, and at each step we are shifting the 1 present in the mask by 1 position to its left. For the result, we check if it is a non-zero number, that means the bit was 1 in our original number, and thus we increment the count. So this was the first method. In this particular approach, how many times are we looping? We would be looping 32 times as we have got a 32-bit integer. Despite of the number being 0 or 1, we always have to check that particular bit in this particular approach. So how can we optimize this? Let's see another approach, which is flipping the least significant 1 bit. In this, we are taking the number and we'll do an AND operation with number minus 1. This operation would give us a result with the flipped bit for the last one that was present in the original number. So this is the least significant one present in our number, and in the result it got flipped. So in each time we are flipping, we will be incrementing our count. So this given number is 11. Its AND operation with number minus 1, which is 10, would give us 10 as our new number. Now we need to count the ones in this new number. So we take it as a num and we do its AND operation with number minus 1, which is 9. And this would give us 8, which is our new number. With this, we'll increment our count as we have already flipped the last 1 bit. Again, we'll do an AND operation, and this time we'll get the number as 0. Now, since we have got 0, we know that there is no 1 present in this particular number, and so we can stop. So, if you see the difference, the number of times we looped in this particular approach is the number of ones present in the number. The worst case for this particular approach would be 32, which is O of 1, but the best case would be the number of ones that are present in the given number. So, these were the two approaches. One was the naive and one was the optimized approach. So now let's go ahead and code it out. So let's start with the first approach, wherein we'll take count and mask. Now we'll take our loop, which would be from 0 to 32. In here, we check if the AND operations give us a non-zero number or not. So we take AND with mask and whether it gives a non-zero number or not. If yes, we do a count plus plus, and then we also need to update our mask. So mask becomes mask left shift by 1. Finally, we return the count. Let's run this code, and it is giving a perfect result. Let's submit this, and it got submitted. The time complexity is O of 1 and the space complexity here is also O of 1. But as we already talked about, it would always loop 32 times. So now let's go ahead and improve this approach. So we'll take a count variable for our result, which would be initially 0, and we'll loop while n is not equal to 0. We'll keep on flipping the least significant set bit. So we do n equal to n and with n minus 1. With this, we'll also increase our count. At the end, we need to return count. Fine. So let's try to run all the test cases, and that is accepted. Let's submit this, and it got submitted. So the time complexity for this is also O of 1. So now we'll try to convert the solution into a recursive call. So for that, we'll take a base condition, that would be our exit condition. If n is 0, we'll return 0. If n is 1, we return 1. And this while loop goes away, and we'll recursively call the same function with n and n minus 1, and each time we also need to add 1. So let's run this, and it gives a perfect result. Let's submit this, and it got submitted. So the time complexity remains the same. We just converted it into a recursive solution instead of iterative one. So that's it for today, guys. Thank you for watching this video. If you want to learn a similar question, you can go for Hamming distance, the link for which is given in the top. I'll see you in the next one.